Right, good day, ladies and gentlemen, yet again, and welcome back to Inside Science Theory. In the previous video on work energy and power, we looked at a brief introduction into work energy and power and what or how the angle of theta changes with time. We looked at the equation for work done. We looked at different scenarios of how theta would change. We also went through the final part, which was on WorkNet. So I just want us to do, just want us to go through another part of work energy and power, which is known as the work energy theorem. Okay, the work energy theorem. Okay, so under the work energy theorem, by definition, it says that the net work done on an object is equivalent to the object's change in kinetic energy. And that's the equation for work net. So the net work done on an object is equivalent to the object's change in kinetic energy. Please do not forget this. This is known as the work energy theorem. Right. And if you further simplify this, you then find that the work net is equivalent to 1 over 2 times the mass times the final velocity of the object minus 1 over 2 times the mass times the initial velocity. Remember, that's what it means for delta K, delta EK. So this, notice that we have a common factor here, which is 1 over 2m. So I can factor that out, and I'm going to have 1 over, oh, sorry, I forgot to square this. It's just so sorry. So this becomes 1 over 2m open bracket v final squared minus v initial squared. Guys, please do not get, please do not confuse, please do not try to change this equation and say v final minus v initial all squared. That is completely wrong. That is totally different from what we have here. From your laws of exponents, you should know by now that you're not allowed to do that. Okay? So just make sure to not make that mistake ever. Okay. All right. And then this is what we have as the work net when we've simplified it a bit further. Right. Okay. Oh, yes. Sorry. Just to also simplify the work net part, just to remember that right now. Remember that the work net is also equal to the net work done on an object times delta x times the cosine of theta. And that's going to then be equal to 1 over 2m open bracket v final squared minus v initial squared. If you don't know where we got this thing here, guys, please make sure to watch the first video before you look at this one. Okay, this is what we have then at the end of it all. Just put this in a nice white box. Okay, so this is what we have. Please do not forget this. You can also rewrite this as the following, or you can say, so moving from work net, moving from this equation over here, you can rewrite this as the work done by the first force plus the work done by the second force plus dot dot dot, which is then equal to 1 over 2m open bracket v final squared minus the initial velocity squared. Okay, once again, if you are confused about what's going on here, please make sure to watch the video before this one, before you come to this one. Just watch that video that comes before this one. So this is one way of writing it. This is the other way of writing it. And please, ladies and gentlemen, in the exam, what you would decide to choose, whether equation one or equation two, would be solely dependent on the type of question you're looking at and the information that you're given in the question. So it isn't a thing of saying you can choose any time. No, sometimes one might not work. So you just need to make sure to consider the information given and how you can use that particular information. Okay. Then the next part that I want us to go through is what we call conservative and non-conservative forces. Conservative and your non-conservative forces. Okay, so your conservative forces and your non-conservative forces are also another part that you need to make sure that you understand, right? So by definition that you should get from the exam guideline, conservative forces is defined as the work done by a certain force in moving an object from a certain point A to a point B, being independent on the path taken, right? So don't stress too much about the definition because you just need to get that from the exam guideline. But in the most basic sense, all your conservative forces are basically your non-contact forces. Remember in grade 11 when you started with Newton's laws, you got introduced to your contact and your non-contact forces. And your first non-contact force, the most basic, is your gravitational force, right? The second one would be any type of non-contact force, like your magnetic force, for example. Another one would be your electrostatic force. You know, there's a whole lot of them. There's a whole bunch of non-contact forces that we have. But in work energy and power, we'll focus mainly on the gravitational force. Okay. And then your non-conservative force is simply defined as the work done by a force in moving an object from point A to point B, being dependent on the path taken. Once again, do not stress too much about the definitions. You should get that from the exam guideline. Right, so with non-conservative forces, in the most basic sense, these are just all your contact forces. So any contact force is then considered to be a non-conservative force. So in this case, your contact force would be your frictional force. The second one would be your applied force. The third one would be your typical normal force, right? And another one would be your tension force. And what other one do you guys focus on? So frictional force, applied force, normal force, tension force, and we'll keep it at these four for now. Okay, so notice how all these forces here are your contact forces, and all these forces here are your non-contact. So in case you forget these things, just remember, contact forces are your non-conservative forces are basically your contact forces, and your conservative forces are basically your non-contact forces. Right. And there is a certain equation that you use to calculate work done by a certain non-conservative force. Remember, we're looking at work, energy, and power, guys. So we're going to talk about work done by a certain force. Each force does a different kind of work on an object, right? But now if we're going to consider the work done by non-conservative forces, then we say that the work done by NC, that's how we denote work done by non-conservative force, is equivalent to the sum of the object's change in kinetic energy and the object's potential energy, right? Remember that the formula for potential energy is the mass times the gravitational acceleration times the height. So in this case, if you further simplify, you would have 1 over 2m, which is v final. Okay, let me just take it a bit more slower. 1 over 2m times the final velocity squared minus 1 over 2. So this is all for the delta k part. 1 over 2m times the initial velocity squared. And then you're going to add that to the mass times the gravitational acceleration times the height, right, of the object. But this is the final height minus the mass times the value of g times the initial height. If you further simplify this, you would get that 1 over 2m open bracket is equivalent to, open bracket v final squared minus v initial squared plus, right, we do the same thing on the other side, we take out our common factor, m times g, open bracket, the final height minus the initial height. And this, ladies and gentlemen, is your equation for the work done by a non-conservative force. Right, remember your non-conservative force, guys. These conservative forces are the forces that are your contact forces, either your friction, either your force applied, either your normal force or your tension force, right? So this is very important to remember. Do not forget this, guys. And another thing you must remember, if you have more than one non-conservative force acting on the object, then your WNC will then be the work done by the first non-conservative force plus the work done by the second non-conservative force plus dot dot dot. So this dot 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 basically means it depends on the number of non-conservative forces acting on the object. So please make sure to not forget this. Let's say the first non-conservative force acting on the object is friction, and then the second one, let's say that's tension, and then there's the third one, let's say that's applied force, right? So your non-conservative forces will be the sum of the work done by friction, the work done by tension, and the work done by a certain other force, say Fa. So do not forget this part, guys. Please, 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 please. Okay, I'm just gonna leave this here for you to not forget this. If you don't forget this, then I promise you all will definitely go well. Right. I believe that's everything. But before I get into doing a past question paper with you guys, I just want to add on to the last part of this, and I want us to focus on um what is this? I want us to also focus on power, underwork energy and power. Remember, we've done the work, the energy part. Now we need to look at the power part of the section. Okay, so let me just quickly write that down. And by the way, okay, I think I'll just mention that as I go into the power part. Okay, so just please remember that if we're looking at power, guys, please remember that by definition, power is defined as the the rate at which work is done, right? So the equation for power that we all know by now is P is equivalent to W over delta T. Okay, this is what we know. This is what power is equivalent to. Okay, so now just a quick thing that we should know by now is that work is measured in joules, right? This is delta T. In physics, we measure time in seconds, and this is power, and this is measured in watts, capital W. Okay, now, guys, I need you to understand something. Whenever we are looking at power, right? And in this case, we talk about average power, but we'll get into that a bit later. But for now, I just want us to look at a certain example. Just do one quick example. Now, say in this example, we are given the following. We are given the first thing that we're given, let's say, is the mass of an object. Right? They say a certain object has a mass of 10 kilograms, for example, and we are also given the fact that there is a height of this thing. So this thing is at a height of 2.2 meters, or 2 meters to be to avoid the whole decimal thing. So 2 meters, right? And also they give us the time and they say this is equivalent to 3 seconds. And then the question says to us, um, the question then says to us, calculate Now the question then says to us, calculate the power. Right. So notice the information that you are given, guys. Right? So you're given the mass, the height, and the change in time. And from the equation that you're given here, which is P equals to W over delta T, you do not know where you can substitute. For example, I mean, where, okay, we already know that we have delta T, but we don't know where we can substitute the mass and the height. So where does that go? That then brings me to my next point. In this equation, the work in the numerator is not just any work, ladies and gentlemen. This is the work done, right? This is the work done. It's not always the case. In electric circuits, we have equations of power, which is a different scenario. But in this case, we're looking at the work done by a certain force. So in this particular case, I'll have the power equals to the work done, right, divided by the change in time. And we know that the work done is defined as the force, right, times the displacement times the cosine of theta. And you divide all of that by the time. Okay, right. Now, ladies and gentlemen, we need to think about this. Okay, so if you think about it, guys, if we're talking about height, what does that tell you? This then tells you that you are looking at an object here that is somehow held by some vertical string. So there is a height, there is some 10 kg object, like they said the mass was 10 kg, that is held above the ground. This is the ground at a height. So this object is basically at a height of h equals to 2 meters. And of course, if we now need to calculate the value of the force, I mean, guys, how many forces are actually acting on this object? Well, we would notice that the force that you would have here would then be the gravitational force. Please always make sure to draw your vector diagrams. So it would then be the gravitational force. So force that we're going to be looking at right now. Now I want you to notice something. The gravitational force acts downwards, right? And this particular object is held at a height of 2 meters. So now the question at hand is, what type of work does the gravitational force do? Gravitational force in this case is then going to do positive work. Because mind you, this object is not being moved at all. It's just held stationary. So the velocity of this object is basically zero. It's held stationary. So there isn't a thing of saying the gravitational force either does positive work or negative work. So in this case, since there isn't any motion or any type of displacement of the object, we then assume that this object, or rather this gravitational force, does positive work, right? The object is not moving, so it does not do any negative work, it does not do any positive work, it does not act perpendicular. So in this case, we just assume that the angle of theta will then be 0 degrees. So in this particular case, what you would have is the force in this case of focus is our gravitational force. And we know that gravitational force is equivalent to m times the gravitational acceleration. So this is then going to be the mass times the gravitational acceleration times delta x times the cosine of theta, and I divide this whole thing by delta t. So in this case, if you calculate and you substitute, you find that the mass of this object is 10 kg, right? So that's what we were given. We were given the mass as 10, yes, and we are given that the gravitational acceleration is 9.8. We all know this. And then the delta x, the height basically, is given as 2. And then we're going to take this as the cosine of 0 degrees. And we're going to divide this by 3 seconds. The final answer that you should get from this should then be the following. So 10 times 9.8 times 2 times the cosine of 0 degrees, and we divide that by 3, I get I get the value of 65.33, round to two decimal places. And remember, this is the value for power, so this should be in watts. Okay, I believe all is well so far. Okay, now I want us to now focus on average power. It's just an addition to this whole thing. So average power. Now, please keep in mind, when we're dealing with average power, we then make reference to we then deal rather with constant velocity. So please keep in mind that when we're looking at average power, then the velocity that we will be working with does not change, ladies and gentlemen. So in this case, now please pay attention. We have the equation for average power, which says that the power average is equivalent to the force times the average velocity, right? Please keep that in mind. So power equals to the force times the average velocity. Sometimes maybe your teachers might have this equation in this form: average power equals to the force times v, and they would have this arrow right there. Okay, if you further simplify this, guys, what do you realize? This is basically velocity, right? And by definition, we know that velocity is defined as the rate of change in time. You learned this in grade 7, the rate of change in position, in displacement, right? The rate of change in displacement, this is then your velocity. So in this case, this, if I substitute that, this is going to be delta x over delta t, which will then be f times delta x divided by delta t. And this is what you would have for your average power. Now, guys, this is not what you stop at. This equation you would use depending on the information you're given. Guys, it's very important to not expect an equation to always stay the way it is, or you always use that equation and no other equation again. You choose an equation depending on the information that you have. You need to make sure that you have sufficient information that will suffice for the equation that you want to use. You can't want to use an equation and have less information for that equation. You will be in trouble because you will not know what your next direction is. So this is an equation for average power that you can use. And the second equation would then be that average power is equivalent to the force times the average velocity. Okay, now just to, before I forget, whenever you want to calculate the value of V average, let's say you want the value of the average velocity, maybe you're not given the value of the average velocity in the exam. Please keep in mind, like I've mentioned, that this velocity is constant, guys. We are looking at constant velocity. Okay, so please make sure that you do not forget that. And to calculate the value of V average, then you use the equation V average is equivalent to the velocity initial plus the final velocity divided by 2. So please do not forget that equation. So whenever you don't have the value of V average and you need it, they can just say V final plus V initial, or then divided by 2, will then give you the value of this guy right there. Right. I really hope that was clear. So I'm just gonna do a quick example with you guys to basically wrap this up. So now in our example, let's say I'm given the following diagram. So I have a diagram here like this. So I have a certain object. So this is my ground, and I have a certain object. So it's a pulley system. that holds an object of a certain mass. Let's say the mass of this particular object is 50 kilograms, right? And this is being held by a certain rope that's attached to the ground like this over a frictionless pulley, right? This is our pulley right there. Okay, so they say that this object is held at a height of, just write that down. So it's held at a height of 4 meters above the ground. Okay, and we are also given the following information. We are also then given that this particular object, right? Okay, what they want. Let's start with what they want. They want us to calculate. Okay, let me just start with what's given. So they give me the height, which is 4 meters, right? And they give me the mass of the object, which is 50 kilograms. Sorry. And then they did give me the change in time. They say to me that the change in time for this object is 10 seconds. Now they then say to me, calculate the power. Okay, so how do we go about this, ladies and gentlemen? Notice something. You will have two equations here. So from the information that you are given, which equation would work best here, ladies and gentlemen? Would it be equation 1 or equation 2? Yes, if you said equation 1, you're definitely right. Why can we not use equation 2? Because in order for us to use equation 2, we would need um, we would need the average velocity, and that would mean we also need to have the initial velocity and the final velocity according to this equation. But we do not have any of that. So we can't go and use this equation. That will not work because we don't have enough information. But if you're looking at equation 1, I do have the change in position. That's my height of 4 meters. I do have the change in time, which is 10 seconds. So of course, by now you can already see that this is an equation that is proper for me to use. Okay, so now we have the following. Now, if you think about it before we jump and try to attempt the question, let's look at the forces acting on this object. So if you think about it, this object is held stationary yet again. So the velocity of this object is equivalent to 0. So if it's held stationary, there is no applied force acting on it. There is no there is no tension force acting on it. There is no frictional force acting on it. There is no normal force, definitely, because it's not on a surface. So the only force acting on this object is then going to be your gravitational force. Okay, so from here I can then say P equals to the force times delta X over delta T. Remember, that is what we have in this equation. But now, since you're looking at the vertical height, I think it's best if we just refer to this as delta Y, because we're looking at the vertical height, guys, remember? And in this case, the type of force that we're looking at is the gravitational force. Now we can calculate. So we know that the gravitational force is basically the mass times the gravitational acceleration. And in brackets, we have delta x over delta t. And the mass of the object is given as 50. And the gravitational acceleration is 9.8. And in the bracket, we have delta y, sorry, which is equivalent to 4 divided by a time of 10 seconds. And the final answer that you should get for power here is, so 4 divided by 10 times 50 times 9.8, and that's equal to 196 watts. That's the power that we got there, ladies and gentlemen. So notice something, guys. I didn't just decide to use a certain equation, right? It all depends on the information that you're given. Please make sure to write down the information that you're given so that you can see from the given information which equation would work best. Do not just try to answer a question because you think it would work. I mean, a certain equation would work. Always make sure to analyze the question first Write down the given information, and from there you can conclude on the equation you can use. Right, I hope that was clear, guys. We will then leave it here for now. And in the next time we meet, we're going to do a post exam question that will basically consolidate everything that we've done thus far. But before I conclude, I just want to add on a couple of things. So in an exam, whenever they say to you, these are typical questions, by the way. So exam type question. Whenever the examiner says to you, using energy principles. Now, this is a common one. When they say using energy principles, this basically means use all the equations that we've done thus far under work, energy, and power, and also include the equations that you've done in your previous grades. So all your work energy principles will be the following. The first one would be your mechanical energy. Remember this equation from grade 11? Yes, it's back. Mechanical energy is equivalent to the sum of the potential and the kinetic energy and the potential energy. Okay. The second one would then be um, the kinetic energy. Okay, right? This is equivalent to 1 over 2m v squared. And then the third one would then be your potential energy, which is then the mass times the gravity times the value of g times h. The fourth one would then be your work done, right? Delta x cosine of theta. The fifth one would then be the work energy theorem, right? And the sixth one would be the work done by non-conservative force. Remember, we've done this already, done the work done by non-conservative force. Okay, so these are your forces that you need to keep in your brain whenever the question says using energy principles. And of course, you have to choose one depending on the type of question you're given, depending on the information that has been provided for you in the exam. That information given will then allow you to easily choose the proper equation to use. So don't just use an equation because you feel it will work. No. Always write down the given information. Make sure that the information you have will then be enough or sufficient for the equation that you want to use. So please keep that in mind, ladies and gentlemen. But for me to you, we'll then leave it here. And again, in the next video, we'll then look at past exam questions as we consolidate work, energy, and power. I really hope everything was clear up till this point. And I will leave you guys and see you in the next video. Good night.